Good afternoon. Welcome, colleagues in Hong Kong Genomic Institute and online. My name is Brian Chung. I am the Chief Medical and Scientific Officer of the Hong Kong Genomic Institute. Of course, you're seeing me because we have the exciting Gene Club. Gene Club, the word gene stands for Genomic Exchange for Nurturing Excellence. So this is one of our major strategies to actually promote the development of genomic medicine in Hong Kong. And today I have great pleasure to introduce our speaker, Professor Guy Chen. Professor Guy Chen is a distinguished academician and clinician specializing in vitreoretinal diseases. He serves as professor in the Department of Ophthalmology and Visual Sciences and head of graduate division at the Chinese University of Hong Kong. He also holds honorary consultant roles as the Prince of Wales Hospital and the Hong Kong Eye Hospital. As a leading researcher in ophthalmic genetics and multiomics, Professor Chen investigates multiple different ophthalmologic conditions, including macular degeneration, myopia, glaucoma, and inherited retinal diseases. His work has uncovered novel disease genes, biomarkers, and therapeutic insights. And he has been widely published in over 220 peer-reviewed journals. He's actively involved and engaged in global ophthalmology, and he has chaired key sessions at major conferences and held leadership roles in Asia-Pacific Vitreoretinal Society. He is well recognized for his contributions, and he has received multiple prestigious awards, including the APAO Distinguished Service Award and the Hong Kong Academy of Medicine Distinguished Young Fellow. His research continues to advance our understanding of eye disease, particularly in prevention and treatment. Today, the topic of his talk is Genetic Eye Clinic and the Hong Kong Children's Eye Genetics Study. Thank you, Professor Chen.
Okay, good afternoon, dear friends and colleagues, and Brian and Dololo and Jackie, and friends in Hong Kong GI and also online. So today it's my great honor to share with you some of our work. As Brian mentioned just now, that I'm a clinician. In fact, I'm working on vitreoretinal disease or macular diseases. So in fact, myopia control, today I'm going to share with you something about myopia. I work on myopia on both clinical side and also the basic science or mainly genetics aspects of myopia. So this title is suggested by, it's a very fancy title, but it's suggested by Dr. Lo. So it's a very challenging, in fact it's a very good topic, very excellent topic. And it's combined, it's a perfect match or perfect storm between the gene or genetic aspect and also the clinical lifestyle aspect of myopia. And I'm Guy Chen from Chinese University of Hong Kong. Yes, I'm also very honored as a recipient of the HKAM and HKGI, the research grant. Yeah. So here's some of our grant supports of the related work, and of course the Hong Kong GI grant is a very important provide very important support to our work. And of course, a special thanks to Dr. Lo, Brian, and also Isabella for all the invitation and all the very fine logistic arrangement. So now come back to the topic. So myopia, you know that is for our normal eye or in normal subjects, so we can see very distant image very clearly, right? While for myopic subjects, I won't call them as patients, but they're individuals or myopic subjects. They without the glasses, they cannot see. They can see near object clearly, but they cannot see distant image clearly. So that means so they need the help of the glasses. So in fact, the mechanism, a very basic mechanism of myopia is that it is due to the elongation of the eyeball, leading to an imbalance between the optical power of the eye and also the axial length of the eye. So that usually in normal eye, the image, the parallel light will focus right on the macula or on the retina, while for the myopic eye, because the eye is elongated, so the image will focus in front of the macula, so that we cannot, for myopic eye, we cannot see the distant image very clearly. So this is when for some other reason or some other mechanism is due to the change or excessive the curvature of the cornea or the increased power of the lens. So this usually in adults, and usually we call index myopia, usually occur in those with cataract in adult, while for children, usually it's due to the lengthening of the eyeball. Okay. So here shows the different severity of myopia. For emmetropia, which means normal, is from hypermature 遠視 hypermature +2 to -0.25 度近視. So these are we define as normal. While for those mild myopia is those who with a myopia greater than 0.05%, 50度近視, we call they are already myopia already. While for high myopia is usually defined by a refractive error greater than -5 or -6. There's some difference between different literature, right? So usually in Hong Kong, in China, because we have lots of myopia, so usually we define -6 600度 as high myopia. And pathologic myopia also is a part of high myopia, but we can see that it's a bulging, the macula will bulge out. Is causing, we call it a posterior staphyloma. So this is a structural change of the shell of the eyeball, so that it can cause some various of complications. So regarding complication, because the eyeball is elongated, so the eye structure are loosened, and you can imagine that the retina is also stretched and become thinning, right? Become thinner. So these stretch of the eyeball or stretch of the retina can cause a number of complications, including retinal break and retinal detachment. I will mention it later, and also glaucoma and cataract and myopic maculopathy. So these as the myopia become more severe, the higher the complication will be, and more severe the complication will be. Okay. So here shows the RD, retinal detachment symptomatic loss. So it's usually due to a break on a break on the retina. So here's a break, and causing the fluid from inside the eye go beneath into the retina, so that can detach the retina. So the patient will see a lot of, this is acute phase, so the patient can see a lot of black dots, floaters, we call Feynman acute floaters, and also a curtain sign. You can see the left upper angle is a curtain, just like a curtain sign, and this curtain will go down, okay? And when the curtain go beyond the middle side, then the patient usually will lose their eyesight, okay? So this is a very acute condition, very severe, and the patient needs surgery, definitely, okay? And for glaucoma, it's usually due to the elevation of the intraocular pressure, and so that have a first stretch of the have a pressure and stretch of the optic nerve, and causing the optic nerve degeneration. And clinically, the patient may have a narrow or constricted visual field, and at one stage, the patient just can have a tunnel vision. Okay, 管狀視, we call tunnel vision. And for myopic maculopathy, is the degeneration of the macula. So please don't think that this is 唔關我事. So this is a elderly subject. Please, here I saw example here from this paper. The macular hemorrhage can occur as early as in the teens. Okay, this patient is 17 of age. Then the patient developed a macular hemorrhage already. So this is not a not a pattern of elderly, but also can have of the kids. Okay, yeah. So for the macular myopic maculopathy, patient can see a central scotoma, 有個孔, and also can distorted central vision, very distorted. So so I believe that many or some of our friends here will ask that, I have performed refractive surgery, right? LASIK or smile surgery recently or before. So now I don't need to wear glasses, right? Including contact lens, right? So I'm very happy that I don't have this risk of complication. So is this a correct thinking? Of course, yes, you don't need glasses. So cosmetically, you get rid of this complication, right? You don't need glasses. But for clinically, because for the refractive surgery, we only work on the cornea. Then we use the excimer laser to shave part of the laser to make the cornea become flattened, so that we change the reflection of the eye. But this will never, this reflex surgery will never eliminate the risk of myopia. So please keep in mind that you, for who those that have after LASIK or smile surgery, you still have the risk of myopia. So myopia, in fact, it is a very severe or very common condition, right? Okay. So this shows a preference of an expected preference. So now, up to now, about nearly 35% of the world population is myopic, and it is estimated that up to 2050, about half of the world population will become myopic, right? So this is even half. I think because the city audience here, I believe more than half. But Hong Kong is another story. Hong Kong, right? This is the global situation. While for the world map, we can see that in Asia, in the Asian population, we bear the most significant burden of myopia. Well, but someone may think that, or in Caucasian, in the West, whether myopia may not be a big problem, but we can see that in the lower boundary is lower, but the upper bound is also near 60%. So basically, it's the global issue, right? Not only, again, not a patent of our Asian alone. So, but regarding high myopia, it's our patent, right? It's a 專利, because now you can see that in China, Taiwan, mainland China, Taiwan, Hong Kong, and other countries like Japanese and Singapore. So high myopia, in fact, is very severe, very high preference, because more than 50% to even more than 20% of our population is suffering from high myopia. While in the West, in Caucasian, usually the high myopia usually occur in less than 5%. So high myopia is a very special issue and concern in our population. And why there's some ethnic difference of the myopia preference? We expect that propose that a number of factors may play the role, including the genetic predisposition. That means an ethnic difference, right? So and also the environmental risk factors or exposure different between Asian and Caucasian or West environment, and also the cultural background or cultural habits, right? So including the intensity of schooling, the intensity of near work outdoor activities, and also some other lifestyle factors. Of course, some other social economic factors, including income and the strata of the income, may also play a role in such differences. So here, all these are composed of the risk factors of myopia, including excessive near work, less or insufficient outdoor time, and also higher education, higher preference of parental myopia, secondhand smoking, and some environment pollution also play a role in myopia development and also the progression. And of course, genetic factors also play a very important role in myopia development and progression. So the evidence of genetics in myopia, we can have a different layer of evidence. Number one is from twins and sibling studies. We know that the heritability of myopia is about 50 to 90%, which is quite high. And in the past 2 decades, a number of large-scale genome-wide study, genome-wide association study, GWAS, have identified over 400 genetic loci for adults myopia in adults, but not in children. So in the past 10 years, since 2015, our team has launched 3 different studies, including the Hong Kong Chen Eye study, Hong Kong Chen Eye genetics study, and also the LAM study, in which we use the low concentration atropine eye drop for myopia progression, for myopia prevention, and to control the progression. So, and 3 years after our launch of our myopia program, President Xi, right, already he gave a very important advice to our nation that myopia, in fact, is a very severe health problem in our children. So we need to protect our children's eye health so that they can have a bright future. So, of course, this will become a very important healthcare policy in our country, right? So basically, different department in the country, they have already set up a very specific goal of myopia control in our country. So that means annually we need to reduce the. This is not easy, right? Because our country has a lot of people, so we need to aim to have an annual reduction of myopia by 0.5%. While for those in high prevalent provinces, our target is to reduce 1% every year. So at that time, in our country, for those for children with 8-year-old, the myopia prevalence was 3%. While in the overall primary schools, the myopia occur in around 40% of the pupils, while for junior high school or senior high school students, these are already quite severe. 60 to 70% of our students are myopic. But in Hong Kong, for those with 6-year-old, our data shows that one in every 4 children they will be myopic. Right? So this is from our own Hong Kong data. So this is why we need to, in the past 10 years, we set one of our focus on myopia research. This include Hong Kong Children Eye Study and Hong Kong Children Eye Genetic Study. So this study was divided into 3 phases. The first phase is called Hong Kong Children Eye Study, and then because in the next 2 phases we have the grant support, very important support from the Majority Club, so we changed the name. But in fact, our aim is not changed, right? We want to beat myopia, basically, right? And for the Hong Kong Children Eye Study, up to now, in the past 10 years, on every weekend, we invite about 100 children from different primary schools in Hong Kong, and also we invite their parents to come to our clinic in Hong Kong Eye, in the 3rd floor of the Hong Kong Eye Hospital, and we perform very detailed eye examination and investigation for all the patients and also for the parents. So this shows me that who are examining the children. So, and also we collect the biosample mainly because they are very young, so we collect a buccal swab sample. But for those elder subjects, we collect the blood sample. And we after the baseline examination, we also invite them back in every 3 years so that we can have their longitudinal data as well. So this slide shows the myopia preference in Hong Kong. In the left panel, their data before the COVID-19 pandemic. So, but by that time, for those of 6-year-old, the myopia preference is only around, not only, but already around 30%. But and the preference increased about 10% every 1 year when they become older, right? Become older. Well, after COVID-19 pandemic, so the preference doubled. So in the primary 1 school pupils, the myopia preference is already 25%. So this is a very severe condition in our population. So we expect that is the suddenly dramatic increase of the preference is due to excessive need work, because during COVID we need a lot of online teaching, right? And also the social isolation the policy. So the children just stay at home and they don't have the chance to go out for outdoor activities. So this is one of the risk factors. And also the education, right? Education is we think is a proxy for more near work and less outdoor, right? So education, and also of course there's some other, the intelligence is also a underlying factor for myopia. And for the secondhand smoking as well, because they stay at home, right? So for those with parental smoking families, so they have a higher exposure to secondhand smoking. So with our data, these are all our paper, that we also find that secondhand smoking exposure is also a risk factor for myopia. So we need to promote the concept that we need to quit smoking, right? And also in families with those with highly myopic parents, that means both parents are high myopia, so that the kids have more than 10 times of risk to get myopia in their life. And also, from every single time point, if the both parents are highly myopic, then in the next 3 years, the kid have a 5 times higher chance of getting myopia every time that we visit the kids. Okay, so that means the parental myopia, which can be a proxy, right, of genetics, is a very important risk factor for myopia development. So this also triggered us to enlighten us to go further to work on the Hong Kong GI genetic study by the first step is to build up a biobank, right? So for those, for up to now, we have already collected over 40,000 children sample and along with their parents, which about 80,000 samples. So for the genetic study, I believe many of our audience on site is you are expert on genetics. So just very brief is that in our human genome we have about 20,000 genes. So basically our work on based on these genes. And this is the basic in the molecular genetics, right? Since the central dogma is from DNA transcribed to the mRNA and then to translate to protein, and the protein can act as an enzyme, structural protein, and then they can determine the phenotype we also call traits. But if something wrong happen in the DNA level, then it may translate into something wrong in the trait or in the protein. So this we call the genetic cause, a very simple schematic diagram for the genetic cause of the disease. Well, so our role is to the backward. So we want to identify the gene variant or gene mutation in the DNA that is related to the disease of interest. So the candidate gene can be divided into disease-causing gene or disease-associated gene. Well, for myopia, we have both Mendelian form myopia and also the complex form of myopia. For Mendelian form is usually due to a mutation in one single gene, but for myopia, I think it's less than 1% of the myopia are due to the Mendelian form. So more than 95% of the myopia are in fact multifactorial or complex myopia. Right. So, for association, for gene association, we need to know about this concept, the odds ratio. Odds ratio means a factor increase the risk of disease for a certain fold of risk, right? So, for example, for the macular degeneration, so like smoking is a risk of AMD. So we just have a cost table and can simply calculate the odds ratio. While for the gene, for every SNP as well, for gene variant as well, it's quite simple to understand that for minor allele, and we just input the allele count into this cost table, and then we can calculate the odds ratio. That means that if the odds ratio is greater than 1, then we say that this allele is a risk allele for this disease, while less than 1 is a protective allele. So these are some types of variants. So the most common type of variant we use is SNP, right? Single nucleotide polymorphisms. Some also include other include deletion, insertion, or copy number variants. So these we can use the whole genome sequencing can provide us all these sort of information. So why we need to identify the disease gene is there's a list of reasons. Number one, that we can know better about the mechanism of the disease, and also we can have a better phenotyping or better diagnosis for disease, because in some eye diseases, but just only clinically, it will be very difficult to confirm the subtype of the disease. But after knowing the underlying gene, then we can have a kind of a genetic level or a molecular level of diagnosis, which can, of course, will be helpful for the doctor, also for the patient, for a further follow-up and treatment, right? And also for a genetic consultation as well. We know when we know that this is the underlying disease gene, then we can provide a better genetic consultation. And how about treatment, right? Gene therapy is one thing, right? And also if we know the genetic background of the patient and the genetic underlying the different diseases of the patient, then we can provide a better follow-up, better treatment plan, which can lead to a precision medicine. So genetic association study, as I mentioned, is to identify a genetic variant which is associated with the disease. It can be at different level. The candidate gene analysis is we have a target, we have one or a few candidate genes. While for GWAS, we just perform a association analysis across the whole genome, right? So for myopia genetics, as I mentioned, both environment, lifestyle, and genetic play important roles in myopia development. But the environmental factor only account for slightly more than 10% of the variance of myopia. That means still the loss of variance still lie in other factors, for example, genetics and some other epigenetic factors. So if I mentioned that genetic evidence, we already have a different layer of evidence. So, and why we need to investigate genetics in children? Because in children, their eye is still growing. So that we can collect their, we can not only collect their cross-sectional data, but we can collect their longitudinal data. So you know that usually myopia, the progression of myopia usually stabilize by the year around 20, right? So if we are recruiting the adult cohort, we have no chance to investigate the risk factor of progression, right? So, but in children, because their eyes are still growing, so we can collect their progression data, and we can explore the underlying factor which may trigger the progression of myopia. And in fact, in our previous study with, this is a global collaboration study in which we include a list of adult myopia loci, and we work on these loci in a group of around 5,000 children. But in fact, we find that these they don't show much positive result. Many of them did not show a result, and some of them only show a very mild association with myopia in children. That means we need to identify a children-specific gene marker, especially in our population. So in the Hong Kong GI genetic study, we have performed. This is the blueprint, and this is our strategy. We want to identify gene marker for myopia, its endophenotype, and myopia progression, and also the treatment responses of myopia. And apart from the Hong Kong GI study, we also include other population, including other population in Hong Kong, Shantou, and also Guangzhou, and Chengdu, Sichuan, right? So these are, we have a nationwide, well, of course, this list will be expanded, and so we have a nationwide collaboration for myopia research. So in the beginning, we perform a candidate gene analysis, and we perform a very detailed phenotyping of myopia of the subject. So we have found some gene variants to be associated with fast progression of myopia, and also some gene SNPs associated with the ocular development, and also for myopia. And also some genes, some genes are associated with axial length and corneal curvature, while some others are associated with anisometropia. Anisometropia are yin-yang. So these are the difference between two eyes. So these are some of our papers. And in this work, we find that in children with different severity of myopia, in fact, their genetic spectrum or genetic pattern are in fact partially different, right? And also progression. This is the first study in the world that we identify three genes to be associated with myopia progression in children. And in this study, we identified two genes to be associated with a change and also the axial elongation. So these were mainly due to the follow-up data, right? So if without follow-up data, we don't have the data of the elongation data or progression data. So these are. So we are continuing to visit, to review the children now every weekend. So based on our previous study, we find that in fact the adults and adult in myopia, the genetics or the gene markers are partially overlap. So only a small part of the adult myopia gene also play a role in children myopia. So but for up to now, we don't have any so-called children-specific genes for myopia. So this is our aim to perform a genomic investigation in our children myopia. So for the GWAS, as I mentioned, that we investigate the SNPs or gene marker across our human genome, and we investigate the association of each of these SNP with myopia as a phenotype, right? So in the past, this can be important because if we can find new gene, then probably we can find new pathway, and again, hopefully can lead to a future better control or better treatment, and even new treatment. So this the table below is for some other systemic disease. So by identifying the new genes, so a new pathway, even new treatment can be developed. Okay. And also the gene environment interaction is also important because, as I mentioned, the myopia have a lot of environment, lifestyle risk factors. So if we can identify the gene and lifestyle interaction, so that we can identify those with high genetic risk, so that we can provide a relatively better advice for the healthcare advice, so that whether we can have any lifestyle modification, so that they can reduce their risk of myopia development and progression, right? So in our first phase of our GWAS study, we include our sample size is not very large. Only in the discovery phase, we have only 1,200 children, while for the replication, we have over 4,000 samples from Hong Kong and from Santao. So this is a Manhattan plot from the spherical equivalent, the baseline spherical equivalent, and this is a baseline of the GWAS Manhattan plot of the baseline axial length. And for the baseline SE spherical equivalent, we have already identified two variants, two SNPs achieving a genome-wide level of significance. While for axial length, they have passed our threshold but not achieving the GWAS level yet. And we compare both GWAS data, and we select 6 of these SNPs showing a consistent trend or consistent pattern or effect of from these two data, and then validate these SNPs in the replication cohort of Hong Kong and Santao. And interestingly, we identify 4 new genes or 4 new loci to be strongly or significantly associated with the error in children. So, and also 2 for axial length. And we then to divide the children into those with mild, moderate, and high myopia, and we analyze again that whether the 4 gene variants are associated with every myopia or only for moderate to high myopia. And interestingly, only the log gene, we find that the log gene is associated with all types of myopia, right? Mild, moderate to high. While for the others, for the MIR gene, and these are the TMN3 gene and also the FAM135B gene, they are all of them are only associated with moderate to high myopia. That means that these genes are specific to a higher or more severe subtype of myopia. So these can be marker for us to work on. That if we can find a pathway and find a method that to control this, the expression of this gene, probably we can at least reduce the risk of high myopia occurrence. Sorry. And we also performed the interaction between the genetic risk score and near work. The process is W hour. W hour is the time that the kids spend on near work, right? So we find that for those spend over 12 W hour, not 12 hours on reading, but W hour means we also need to calculate to take the near work into consideration. So 12 W hour usually equivalent to 4 hours of reading a day, right? 4 hours. Okay, so we find that for those with high genetic risk score, and if they spend over 12 W hour a day, then they have over 4-fold of increased risk of getting myopia. Okay, so this is quite high. That means that if I only bear these 4 risk allele or genotype, and then the kids spend 4 hours a day, then their risk of getting myopia is much higher than those with low genetic risk and spending less time on reading. So this chart also shows that the higher the genetic risk and the higher number, the longer near work they perform, the higher risk of myopia they would be. Okay. And we also compare the adults cohort, and we only find that 2 of these 4 variants are associated with myopia in adult, but the other 2 were not associated with myopia in adults. That means we further prove that the genetic profile, in fact, are partially different between children and adults. And also we compare with global data, and we compare with the largest European GWAS data on myopia, and we find that only 20% of the SNPs showing a consistent trend of effect, while for the other nearly over 70%, they either send no effect or different trend of effect. That means in our Chinese, our genetic, the myopia, the genetic profile overall genomic profile of myopia it is largely different from that in Caucasian. So this leaves out a very large room for us to further work on myopia genomics in our own population. So this paper, with the support of the Hong Kong GI grant, so we have published this recently in May this year. And now, so this data, although it's very prelim data or very prelim finding, we only find 4 variants, right? But of course, with we're now recruiting more sample, and we work with Dr. Low and work with Brian. So hopefully, we can identify more new genes. Then this model can be increased. I mean, the risk prediction can be increased, and also the prediction power can also be increased. And so simply based on our own data currently, so we can provide a suggestion after we say, for example, we test the kids, and we know that we can categorize the kids into high genetic risk, medium, and low genetic risk. And for those with high risk, then we will advise them you should read. We encourage them to study well, right? But we encourage them to I will tell them how to prevent or how to reduce the risk, right? But for those relatively low genetic risk, then the reading time can be lengthened, can be longer, not lengthened, but can be a bit longer. Don't look down upon this 1 hour difference, right? This can increase you remember 4 times of risk of getting myopia in children. Okay, yeah. So how to prevent? Okay, so I believe many you are very young. So, but let's say for my kids, right? How to control for prevent or control myopia. So for prevention, right? So we need to have a correct reading posture and distance. So usually we recommend at least 1 foot 1 尺, right? 33 millimeter, or usually I would suggest 40 millimeter, 40 centimeter, sorry, 40 厘米 1尺. And also reading control is don't read. We need to control reading time. This is not for one whole day, right? Because one single time span, right? That means please don't read a book as long as every 40 minutes you need to take a break. Okay, you need to take a break. So this for reading will be easier, but for playing games will be more difficult, right? So as parents, you need to. Of course, every kid come to our clinic, we will give this education to the kid and also the parents. The parents, I think, is more important, but the kids cannot control themselves quite well. And also, we need to increase the outdoor time. And this outdoor time. Outdoor time, that means outdoor time means go out under the sun, but never stare at the sun, right? Never look at the sun, but play under the sun, under sunlight, right? So don't go to the gym. The gym room, gymnasium is not that useful. That means you need to go outside, outdoors, okay? Yeah. And also have a regular vision check, because in the RTHK program this Monday, I shared with the public that how to identify, I can share with you later if you're interested, how to identify the kids who may become myopic. Well, for how to slow the myopia progression, we have different methods. One very important method is that we need to let our kids to wear right glasses, nothing else, right? Because if you don't wear a correct or right glasses, then the myopia is very easy to progress. Not other some whatever fancy method. That only a correct glasses is very important for controlling myopia progression. But for some others, we have a different design of the lenses. For the dim lens, that means you can see a lot of small lenses mount on the routine glasses. Contact lens as well. Contact lens, the OK lens which is wear at night during the nighttime, bedtime, and then remove during when they wake up. So these we call this optical method. Well, for the pathologic method, we have atropine eye drops. I think some of the parents here, your kids may be using atropine, right, from our clinic or from private clinic. So atropine eye drop is also a very useful method. And also nowadays we have some other combination of different sort of these methods. So all in all, is that the increased outdoor activity is the most cost-effective way, right? Just let the kids to play outside, right? This is very important, and I would say it's the most important factor to control myopia. But it's not that easy, right? Because we know the situation in Hong Kong or in many places of the world that 2 hours of outdoor time is difficult to achieve every day, right? So this we need some additional method. For example, some optical correction, some specific design of the lenses, and of course, atropine. I think atropine for now, during all of our studies, we found that atropine 0.05% of atropine is the most effective way to control myopia onset and control myopia progression. So in our study, we find that atropine eye drop can slow myopia progression by nearly 70%. That means how to understand this data is usually for a kid of 6-year-old, usually if they are already myopic, then usually every year they will have a -5 to 1 diopter of progression, 50 至100度嘅 progression. But after using the atropine, on average, annually, they will only have a 30 度 progression. Okay, so these are 70% of reduction of progression, and these are some of the papers supporting our finding. And 2 years ago, we published a article in JAMA, right, that we use atropine to prevent myopia onset. So this is a very new and very daring attempt that we use atropine in those kids who were not yet myopic, right? So this is a preventive medicine, right? But those kids are not a very routine kid. Those kids are high-risk kids. That means both of their parents are myopic, right? So this is why the parents will allow the kids to use the eye drop, because their parents they own are highly myopic. So the kids, they know that they are also at a very high risk of getting myopia later in life. So they agree, and we find that atropine eye drop can prevent myopia onset by 50%, by half. Okay, over 2 years' time of follow-up. So this is a very important method. Important data supporting the role of atropine eye drop in myopia prevention and progression. So this is our estimation that the 0.5% of atropine eye drop can, in the long run, for each generation, right? Not for us, right? For the younger generation, for each generation, they can reduce myopia onset by around 50%, and also retard the myopia progression by nearly 70%. And in the long run, when they get older, when they go up to their adulthood, then we expect that we can reduce in the society, right? We can reduce myopia by 50%, and we can beat high myopia by about 95%. So this is very important, right? Important preventive modality for our kids, and also for the economic aspect. Then for each generation, then we can reduce a number of the complication, a very good number or percentage of the complication, so that we can save a lot of money for the social healthcare system. Okay, yeah, and by performing a meta-analysis, we also proved that 0.05% of atropine eye drop and outdoor activity are the most cost-effective manner for myopia control. So these findings are supporting the role of, again, the atropine eye drops and outdoor activities. So for the atropine eye drop, in fact, we also perform a GWAS for our lemon sample, and also we are now validating in our LEM2 is a prevention, LEM1 is for myopia control. So this is the main plot of the LEM GWAS. And we are now still validating the data. So hopefully we can share with you. If I have the chance, I can share with you in our future sharing about our data. Lastly is another achievement. So, I think some of you may have heard this before. It's a repeat low-level red light therapy. Okay, that means if we use this machine, and it will project a certain wavelength of red light, and the kids will perform twice a day, and each time 3 minutes. 3 minutes. So if they are using atropine, then we can tune down the red light. This is tailor-made for them, right? So these are our data is very encouraging. So for these are only two examples. One example is a 8-year-old kid. Then when we saw him the first time in 2020, he had a -3.2 diopter, 300幾度, okay? And then he's already used a very high use atropine already, but his myopia keep progressing, and up to over this next 4 years, he become a highly myopic, 650度, okay? And so that means he is not a good responder for atropine. But there's no, but we cannot expect that if he did not use atropine. So how high of myopia that he would get over the 4 years, right? But after he used red light, very interestingly, his myopia get slightly revert. That means the myopia 淺咗75度, okay, over only 6 to 9 months of treatment. So that means the myopia get less severe, okay? And this another the girl, that a 7-year-old girl that we perform a press con for this treatment, is that this girl, when she had a -1 diopter before, right? So she need to wear glasses to school before, but after using 4 months of red light treatment plus atropine, then her myopia reverts to 0. That means she doesn't need glasses anymore now. So this is very intriguing or very encouraging finding that for atropine and red light therapy, in fact, the myopia can be reverted in not all, right? But in many of our subjects. So we are now organizing the data, so hopefully we can publish this work maybe earlier next year. Now we are recruiting the performing follow-up for the last batch of our subjects. Okay, but for red light, is it an ideal therapy, right? It's very good, right? It can revert the myopia, but it has some potential risk because some paper find that there's a cone photoreceptor density change in some children use red light. So that means if this risk is particularly high in those kids with potential inherited retinopathy, right? For healthy kids, this should be okay. But for kids that have a risk of like RP, 夜盲症, okay? So these red light, the kids is not suitable for red light. Otherwise, their RP, their 夜盲症 can occur much earlier. So how can we identify this subject at risk? Is we need to have a genomic investigation before the red light treatment. This is ideal. Now we cannot provide this service for our kids, but in the long run, especially with the completion of our Hong Kong Genome Project, that at least and also if the kid is involved in, then we can know that they are genetic background and also whether they also bear the genetic risk of inherited retinal diseases. So for this, we should find some they should not take red light as something. But of course, atropine should be okay, right? So these are for for myopia, children myopia control that the WGS and also nowadays we are AI, deep learning AI, the model, right? Combining different lifestyle factor and also the genetic factor can also provide us a more powerful platform to control and prevent myopia. And go broader is for different eye diseases is also I think the Hong Kong GP or Hong Kong GI is playing a very central role. Is that because you can link up the Hong Kong GP, the Hong Kong Genome Project can link up the disease, link up patient, and link up with the lab, right? And then we can know the genetic factors or pattern of each individual. Then we can stratify, we can grade them based on their genetic risk into low risk, medium to high risk, right? Then we can provide the information back to the hospital and eventually go back to the patient so that they will know that they can have a better estimation of the risk of different eye diseases And of course, if we have the risk assessment, then the doctor can plan a better follow-up time schedule, and plan better treatment in much more advanced before the disease getting worse, right? So this, I think the Hong Kong GP is a very meaningful project, right? It's a meaningful project as me because of I'm work on both clinical and genetic side. So and hopefully why I work on myopia is a joke that I want my job to be more released, right? Because I'm now taking too many of the patient of retinal problem, macular problem, right? So if we can beat myopia, we can reduce myopia from childhood, right? Then our job can be much easier. Yeah, of course, our future, right? Our future generation, they will enjoy a better eye health, right? This is our most important goal for our the young generation. So lastly, I would like to thank my team, right? Professor Kevin Pang, Professor Jason Yam, and our team, and also the support of our chairman and Professor Kevin Tam, and all our colleagues in HK and also from different hospitals, Peter H, Hong Kong Eye, Children's Hospital, and our CUMC, right, next door. And of course, I would like to thank Dolo, Brian, and colleagues from Hong Kong GI for your important support to us. And hopefully we can continue the collaboration on myopia, genomics, and also genomics of other eye diseases. Thank you very much.
Thank you, Professor Chen, for this great talk. And all of us agree completely that this is important work with good scientific discovery of public health impact. It's not just benefiting kids and adults in Hong Kong, but also globally, especially for China as well, because this is one of the most important health initiatives being developed in China. And just some advertisement, Professor Chen also mentioned that he has helped us to give good interviews and talks in RTHK. That's 精靈一點, because we have a series on genomic medicines, especially highlighting on genomic medicine development in Hong Kong. So if you're interested in Professor Guy Chen's interview, please visit Hong Kong Genome Institute LinkedIn sessions. So I always have the privilege of starting to ask a few questions. But before that, Professor Chen, I'm very interested in the red light therapy. And I know that now you're proposing perhaps we need to do genetic screening for retinitis pigmentosa before starting. Just to let you know that in collaboration with the University of Hong Kong Ophthalmology, we have developed strategies to effectively screen for RP genes in our cohort studies. So if there is any room for collaboration, we can certainly help you to do the pre-treatment screening for retinitis pigmentosa before you actually start on that. We already have a protocol to start that. So my questions went back to the earlier part of your presentation, which is very intriguing. We see a lot of increases in myopia during the COVID period, and one of the very important risk factors is the exposure to smoking in the households, because everyone is at home. Do we know why smoking is particularly harmful to eyesight? Of course, we all know that smoking is bad for your health in general. Is there a postulation or a theory behind why this is bad for kids' eye development? I'm looking at your genetic studies, and you focus a lot not just on genetics, but genetics environmental interaction. Could we perhaps study your data sets and understand a little bit more how that is causing the problem?
Yeah, thank you, Brian, for the very important question. So during the smoking, secondhand smoking, we don't know we don't know exact mechanism yet. But usually, because for myopia progression, as I mentioned, is due to the elongation of the eyeball, and elongation of the eyeball is usually due to. Let me come back based on the smoking question, and let me share with you the red light and also atropine treatment mechanism, which are not very clearly yet. But we can combine it as a thinking, right? Because atropine and red light, it is supposed to increase the choroidal blood flow. Choroid is the vascular layer between the sclera and the retina, right? Or we have RPE layer. So the choroid is provide the most blood flow and oxygen supply to the sclera and also to the first few layers of the retina. So we think that the red light and also the atropine can increase the blood flow. And some animal model already approved this phenomenon. So we think that because of smoking, right, smoking usually can, we also find that the choroidal layer is thinner. So that means don't look down upon the secondhand smoking, right? Secondhand smoking, but to the kids because they are still growing, right? So they're very sensitive. The receptor can be very sensitive to the substance in the smoke, right? The smoke. So we expect that the choroid can be go ischemic. So if the choroid is go ischemic, then the sclera can go a hypoxic status, right? Hypoxic, that means that they can, when they go elongated, they cannot come back. Right, they become more rigid, right? So become more rigid and more, so that these can be one of the explanation to link up smoking and myopia progression. Yeah. Yeah.
So this is a very important environmental risk factors, even for vision. So the question and answer sessions is also open to the floor, but may I also take this chance to remind colleagues and friends online, you can type in your questions and then we can help you to ask.
So what are the mechanisms behind those, let's say the loci that will predispose to the developments? So what kind of pathway that may these loci affect?
Yes, thank you, Jackie, for the very important question. This question, in fact, is our next step of work. Of course, after, as you know, after the identification of the genes, that the next step is to look at the expression of this gene in different parts of the eye and also their function. So, to be honest, the exact functional role is not known yet. But for these four genes, by bioinformatic analysis, this gene can affect the expression of the gene, number one. Second is they are co-localized with some other diseases. For example, one of the genes is associated with microphthalmia. Microphthalmia means a smaller eyeball at growth, smaller. That means this is the other way around, is the elongation of the eyeball. So that the role is just the gene may control the growth of the eye. And some of these genes are basically all of these genes are expressed in RPE. RPE is a layer just underneath the retina. So we think that RPE layer is very important in the pathogenesis of many eye diseases, not only myopia. Right? And yes, and one of these genes is associated with education attainment. It's very interesting. So education alone is not only that the kids spend more time studying so that they are getting more easier to get myopia, but in fact, the gene colocalization also proved that or support that education attainment is also maybe an independent risk factor for myopia. So these can provide some of the hints that this myopia gene, although they have not been associated with myopia before in the kids, but they did have some role in other phenotypes that related to the myopia development. Yeah, very good question. Thank you.
Thank you very much.
Thank you. So perhaps Professor Chen, our collaboration may shed some light on the questions from Professor Jackie Lambs too, because we employed whole genome sequencing here in Hong Kong Genome Institute, and the non-coding part of the changes may actually affect expressions of some of these genes. So we're going to see interesting results. So we have one more question here.
It's just a coincidence that I also have two kids reaching 6 years old, this year, and I'm also have a high myopia. And my wife have myopia, so we are defined as maybe the risk family. So I just like to ask. With your beautiful data, you already showed that atropine treatments prevents the development of myopia in kids from the risk families. But in your following study, you also show us that there are some genetic factors that affect the effectiveness of the treatment. So, according to your most recent, hypothesis or treatment plans, do the kids now, will you recommend them to receive a genetic, testing before receiving the atropine treatment, or you will still recommend atropine treatment for all the kids from at-risk families to prevent myopia? Thank you.
Yes, thank you, Mr. Wang. This is a very important question. This is, in fact, what our GWAS on the LAM1, LAM2 sample would aim to answer. So, our prelim data shows that Sorry, I didn't show the data here, but we have identified about 14 variants, a few variants, so that we calculate the progenitor risk score, right? And also, again, just to categorize them with high risk, low risk, and high risk, medium risk to low risk. And we find that for those with how we certify the patient is a non-responder and a responder, right? Non-responder means their myopia keep progressing, right? At least minus 550 per year, right? For those so-called good responder is less than this, right? This threshold. And then we compare their GWAS data. And we find that for those carrying a higher genetic risk, then they are, of course, they will be defined as more likely to be a poor responder. And interestingly, because in our LAM study, LAM study, we use 0.05%, 0.025%, and 0.05% of atropine. We use a placebo, right? Before use of free concentration of atropine. And our data shows that for those carrying a high genetic risk, then if they use 0.01% of atropine, they are not new response. That means if they're high risk, so they don't have a good response to atropine, but they can still have a fairly okay response, not as good as those with low risk, right? But for those with high genetic risk, they still have a certain amount of effect if they're using 0.05% of atropine, right? So you will ask, so why not all kids start with 0.05? Yes, this is good thinking. This is good proposal. But in our clinic, we see that many of the kids cannot tolerate 0.05. Right? This is a reason. This is a clinical reason. Because I have some kids patient as well. So I have the two brothers, my patient, not my own kids. So the elder brother cannot tolerate 0.05. So he will complain that I cannot see, I cannot do my homework. You think that cannot do homework is very big problem. This is real, right? So I have to reduce his atropine to 0.01, and then he's quite okay. And after 2 years follow-up, his myopia did not progress, right? While his younger brother, which 2 years older than him, he can tolerate 0.05 very well. So they use separately. Usually. So we prescribe a bottle. Those are isolated bottle, right? That minimum, right? So it's more than enough for two brothers to share one single bottle, right? But they cannot share because they need to use a separate concentration. So our data shows that for those with a high genetic risk, then they should use a higher atropine. So and then you ask the next question: if the kid has a high genetic risk, but he cannot tolerate 0.05 atropine, so then we have red light, right? So we have red light. So red light can provide hopefully additional treatment effect, right? But the question come back to Brian that. How about, we don't know, right? We don't know his genetic background, right? We don't know whether he has a risk of RP, right? You know RP, right? Retinitis pigmentosa, night blindness, right? So if he has the RP gene, so if we use a red light, then we will trigger the onset of the RP or the macular dystrophy. So this is another very big problem, right? The patient cannot see, right? So myopia is no longer an issue for patient with RP, right? Although if we can still use atropine, but not red light, right? So these are the strategy. You are very right that if we have the condition, we have the we have these support that we should do for every single one kid when he come to us or she come to us, then we should have a genome test, right? To number one, to see whether he or she carry these RP genes or macular dystrophy genes, right? So if not, then he or she can be very safe to start his or her atropine plus or minus red light, right? And of course, with the genetic data, then we can know that whether they are number one, they are at high risk of myopia development or progression, and second is whether they are good responder or poor responder, right? So these are with the genomic data, we have a lot of assessment that we can perform, and we can predict. And it's very quick, right? It can be very quick. So
Can be very quick.
It can be very quick.
And
yes.
in fact, one of the questions from online is related to usage of genetics information. Can genetics be used to predict complication like retinal tear?
Oh, retinal tear, yes. Yes, I would say like this, because in the data, it shows that about 30% of the RD retinal tear and detachment is due to related to myopia. But honestly, these are from some paper, but in my clinical experience, over 50% of these are related to myopia. So basically, you can see that almost all my patients with RD, right, detachment, they are myopic, right? So basically, not even 50% is a very conservative estimation already. So I think for RD for now, according to my knowledge, there are not many genes of RD. So I can answer you this question quite simply that for now, at least for now, we don't have a gene testing for RD or for retinal break, right? But if we can predict, as I mentioned, if we can reduce 95% of myopia occurrence in the future in this young generation, then I believe that most of at least 50% of RD can be eliminated. I would say. Yeah. So again, it's the issue of myopia. Yeah.
Thank you so much. I think all of us need to thank Professor Chen again. As an audience, you always love to hear Professor Chen's talk. As adult audience, we always gain some new knowledge. And even for kids, because now they have a reason to tell their daddy and mommy when they ask him to study or ask them to study, they said that a professor in eyes tell us that we shouldn't study more than 4 hours a day. Thank you very much, Professor Chen. Thanks a lot. So lastly, I'm going to just do some promotion for the next Gene Club. So this is going to be in October the 10th. Now we're going to learn something about our heart, about cardiology. And Dr. Derek Lee is going to talk to us about the genomics of cardiomyopathy in the next round. Stay tuned with our Gene Club. Thank you very much.